Welcome to this guide on statistical hypothesis testing. Today we are breaking down three foundational tools in data science and statistics: Pearson's chi-squared test, Fisher's exact test, and the Wald test. When we run experiments, collect survey data, or build predictive models, we are constantly faced with a core question. How do we know if our data is actually revealing a real trend, or if we are just looking at a fluke? To separate signal from noise, we rely on hypothesis testing to generate a metric known as the p-value. Simply put, a p-value measures the probability of observing data as extreme, or more extreme, than what we actually collected, under the assumption that the null hypothesis is completely true. In other words, it tells us how surprising our data is if nothing interesting is actually happening. Let's begin with our first method, Pearson's chi-squared test. This test is a staple when you are dealing with categorical variables, and you want to know if they are independent of one another. For example, is a patient's recovery rate independent of the drug treatment they received? To understand how it works, imagine we organize our data into a grid like this one, a contingency table. Here we track the observed counts of successes and failures across a treatment group and a control group. The intuition behind the chi-squared test is straightforward. We start by calculating what the counts should look like if the treatment had absolutely no effect. We call these the expected frequencies. Then we look at our actual data, the observed frequencies. The chi-squared statistic is calculated by taking the difference between the observed and expected values for each cell, squaring that difference to remove negative signs, dividing by the expected value to standardize the scale, and summing them all up. If our observed data is very close to what we mathematically expected, our chi-squared value will be tiny. But if our observed data deviates wildly from the expectation, the statistic grows larger. To find our p-value, we map this calculated statistic onto a chi-squared distribution curve. The shape of this curve depends on our degrees of freedom. The p-value is simply the area under the curve in the far right tail, starting from our calculated statistic. If that red area is incredibly small, typically less than 5%, we reject the idea that the variables are independent and conclude that something meaningful is going on. But Pearson's chi-squared test has a major limitation. It is an asymptotic test, meaning it relies on a mathematical approximation that only holds true when you have a reasonably large sample size. A common rule of thumb is that if any expected cell count drops below 5, the chi-squared approximation falls apart. So what happens when your sample size is very small, or your data is highly skewed? That is where Fisher's exact test comes in. Unlike the chi-squared test, which estimates probabilities using a continuous curve, Fisher's exact test calculates the exact mathematical probability of your specific data layout. It does this using the hypergeometric distribution, which is based on combinatorial math, specifically factorials and binomial coefficients. Look at this formula. By evaluating the combinations of our row totals, column totals, and grand total, it gives us the precise probability of obtaining the exact arrangement of cell values, labeled A, B, C, and D, purely by chance. To calculate the final p-value, the test doesn't just stop at your observed table. It mathematically generates every single alternative table configuration that could possibly exist while keeping the outer row and column totals completely fixed. It then isolates all the tables that represent an even more extreme imbalance than yours, calculates the exact probability for each of those tables,